Greetings and welcome. Thank you for joining us this evening for our first Social Sciences Virtual Faculty Roundtable event of 2021. My name is Tara McCullough, and I'm Associate Director of Development for the Social Sciences in the College of Letters and Science at UC Berkeley. Tonight's event will be a conversation with Professor Kurt Cuffey, who holds the Martin Distinguished Chair in Ocean, Earth, and Climate Science at UC Berkeley. Before we begin, I'd like to thank those who have supported geography at UC Berkeley, including physical geography, Professor Cuffey's area of focus. I want to give special thanks to Gray Brecken and Bob Klabowski for their outstanding support of the geography department. I'd also like to thank our Charter Hill Society members whose leadership giving to our departmental annual funds help sustain our 15 social sciences departments and programs. Before we get started, I'd like to mention a few housekeeping items regarding this Zoom event. All attendees will be muted during the event. For optimal viewing, we recommend that you set your Zoom to speaker view during the presentation. After the talk, we'll have time for Q&A. Some questions were submitted by participants in advance and will be addressed during the presentation. If you'd like to ask a question during the talk, please submit it through the chat feature. There should be time to answer a few questions during the Q&A. Professor Cuffey's presentation will be recorded and will be made available after the event. We'll stop recording after the formal presentation and will not record the Q&A. So now I'm honored to introduce Professor Robert Rue, Chair of the Department of Geography, who will say a few words about the department and will introduce our featured speaker.
Thank you very much, Tara. As the chair of the Geography Department, I'm very pleased to introduce our distinguished faculty member today, Professor Kurt Cuffey, for tonight's roundtable event. Now, before introducing Professor Cuffey, just a few words about our department. UC Berkeley's Geography Department was founded 123 years ago in 1898. Now, that makes us the oldest geography department in the country and one of the oldest in the world. Now, a lot's changed in the discipline of geography, but one near constant is that UC Berkeley has been a leader in shaping this field. Berkeley is often ranked as the top geography program in the United States and one of the top 5 in the world. And this is really quite remarkable given the fact that we only have 13 regular faculty, while the other top 10 departments in the world have 2 to 3 times as many. Now, the reason why we punch so far above their weight is because we have such distinguished and influential faculty like tonight's speaker. So Professor Kurt Cuffey is a renowned glaciologist who specializes in geomorphology, glacial dynamics, and paleoclimatology, all linked together through a theme of ice. And one of his early discoveries that really changed our view of the global climate was his insight on using borehole temperatures in ice sheets to calibrate what is known as the oxygen isotope thermometer. And with this new calibration that he developed, he demonstrated that the temperature change from the last glacial to the Holocene, which is the modern epoch, was much larger than previously believed. Kurt's other research is very impactful with over 50 articles in the top scientific journals and over 8,000 citations. He co-authored the very influential 2006 National Research Council Critical Review of Paleoclimate Science that demonstrated how modern climate change is unlike the natural climate variability that happened over the last 2,000 years. Kurt also wrote the authoritative modern textbook in glaciology, his textbook, The Physics of Glaciers, which is already a classic in the field. Now, Kurt's won numerous awards for his research, more than I can describe or have time to describe today. But I did want to add that he is also a very stellar instructor for geography, recently winning the division's Outstanding Teaching Award. Kurt's also been a leader with the department, serving as department chair for 6 years from 2007 to 2013, shaping the department to what it is today. And he also has a joint appointment with Earth and Planetary Sciences. Now he holds the honorary chair, the Martin Distinguished Chair in Ocean, Earth, and Climate Science. And today he'll be presenting The Past Illuminates the Future, Geophysical Analysis of Past Climate Changes in Antarctica Informs Predictions of Global Warming. Here's Professor Cuffey.
All right. Hello. If everybody can hear me, please raise your hand or gesticulate in some way. Okay, excellent. So let me pull up my lecture here. There we go. You should see a glacier and a mountain as an introductory slide. All right. So our planet is habitable only because of the natural greenhouse effect. That is, certain gases in the atmosphere and condensate in the atmosphere trap radiant energy that is emitted by the planet. And that consequently warms the planet's surface. It's just as though you're lying in bed on a cold winter's evening and you pull a blanket over yourself and you warm up. And the more blankets you pull over yourself, the warmer you get. Same is true of the natural greenhouse effect and unnatural greenhouse effect. This was recognized in the mid-19th century on a physical basis, as indicated by this beautiful quote by John Tyndall. Let me read it. As a dam built across a river causes a local deepening of the stream, so our atmosphere, thrown as a barrier across the terrestrial rays, produces a local heightening of the temperature at the Earth's surface. Okay, here is a plot of global average temperature changing on a year-to-year basis from around 1880 to 1980. And you can see there's a slight warming trend. And what I want to do first is introduce you to two special years here. One is 1896, the other is 1979. By the end of the 19th century, the measurements of spectroscopic properties of molecules had improved to the point where the following prediction was made by Svante Arrhenius, a Swedish chemist. He said that if we double, or if the atmospheric CO2 concentration, the carbon dioxide concentration doubles, global warming of about 5 degrees centigrade is expected. And that was a prediction made in 1896. That's the import of that year. Another thing that happened in the 19th century was this guy, Abraham Lincoln, founded the National Academy of Science. And the National Academy of Science was founded in order to provide independent, objective advice to the nation on matters related to science and technology. The second year, 1979, that was the first time that the US National Academy of Sciences spoke to this question of global warming induced by rising carbon dioxide in the atmosphere. It was a report authored by Jewel Charney of MIT and colleagues. And they concluded that a doubling of the atmospheric CO2 concentration would raise the global temperature by between about 1.5 and 4 degrees centigrade. And so this is the temperature history going up to 1980. You know what happened next. There is a substantial rise in Earth's temperature, apparently inexorable, and continuing at present. This was predicted. So too were some of the escalating impacts of this change on other aspects of the environment. And my favorite example of this was done by a glacial geologist named John Mercer at Ohio State in 1978. And let me read this quote. He said, "One of the warning signs that a dangerous warming trend is underway in Antarctica will be the breakup of ice shelves on both coasts of the Antarctic Peninsula, starting with the northernmost and extending gradually southward." And this claim that was a prediction 50 years ago became reality within about 30 years. What you see here, this is a satellite image of the Antarctic Peninsula and a large floating ice shelf called the Larsen B ice shelf. Here on the right is a scale bar. There's 20 kilometers to give you a sense of the size. And this is an image that was taken in January of 2002. Let me show you the same image with the labels removed. And the very next image was taken only 3 months later. What you witness is a complete disintegration of the core of this floating ice shelf. And that was caused by warming summer temperatures that induced a lot of extra melt at the surface that then caused fracturing of the ice. At the same time, this glacier that flows into the ice shelf, it started flowing faster. What's shown in this diagram is how fast that glacier was flowing as a function of distance. First before that collapse happened, and then after the collapse happened. And you could see the flow increased by almost a factor of 10. And that increase of flow is transfer of ice from the ground out to the ocean. that represents a sea level rise. This is being driven by increases of atmospheric CO2 concentration, largely because of fossil fuel burning. This is a plot of the CO2 concentration in the atmosphere over the last millennium. It was pretty steady and then started to rise with the Industrial Revolution and then rose at an increasing rate. I use this plot in particular because this was a figure that was published in 2001, almost 20 years ago. And this end of the plot here, that was prediction. But now, 20 years later, we can say, where are we? Well, we have recently passed 410 ppm concentration. So that prediction was more or less spot on. And what is going to happen in the century ahead is frankly terrifying. The details depend on how rapidly we burn fossil fuel, but the rise of CO2 concentration will be extraordinary. And this is only going up to the end of the current century. Beyond that, if we continue just to burn all the fossil fuel we have, the CO2 concentrations will return to levels not seen since the age of the dinosaurs. So the big question is, what will be the effects of that increase of the greenhouse effect on the rest of the environment? How large will the climate warming be? What will be other effects on the climate, such as changes of precipitation and possibly, for example, drought in places like California? So in order to answer this question about how the Earth is going to respond to this remarkable unnatural experiment, we need to understand how this geophysical system behaves, how it behaves as a machine. And in order to do that, first of all, we need to have a sound physical understanding of the mechanisms involved. But that kind of theoretical understanding by itself is never sufficient. And as in any science, in order to advance the science, to deepen the understanding, there needs to be an interaction between theory and observation, There is unfortunately, well, actually probably just as well, no way to take the Earth into a laboratory and perform controlled experiments on it. But what we can do is use the past history of environmental changes on Earth to, as experiments, as natural experiments. And this I refer to as the paleoclimate imperative. It's a demand that we take seriously past changes in our planet's environment because they reveal to us aspects of the changing environment and, more importantly, the system itself, how the system behaves. So let me just give you one example. This is a climate of the last 10,000 years in central Greenland. And what's shown here are two aspects of climate, the temperature and the snow accumulation going from 10,000 years ago to present. And the last 10,000 years, of course, is the period in which civilization developed and thrived. So now let's extend our view back further in time and look at the magnitudes of changes that you see. The planet has been capable of some enormous changes. And this is, in some way, this capacity for change, in some ways, is horrifying, but it's also an opportunity to learn about the climate and environmental system. In other words, to answer that question, how does the geophysical system behave as a machine? Those big changes happened because the planet was in a very different state and transitioning from that state to the modern, relatively warm climate. That different state was the last ice age. So 20,000 years ago or so, the entirety of northern North America was covered by glacial ice. It's called the Laurentide ice sheet and the Cordilleran ice sheet. So the site that's now Boston was under 1 kilometer of ice. The site of Seattle was under 0.5 kilometer of ice. And the edge of the ice sheet was at New York City, depositing sediment that would then become Long Island. And this is a tremendous change compared to present in the planet that allows us to ask questions about how the planet evolved. So I'm specifically going to focus on a question that is, how cold was the planet at the last glacial maximum? That is 21,000 years ago when the ice was at its greatest extent. And the reason for focusing on this is severalfold. One is that it indicates how much does the climate change in response to major changes of certain climate driving factors, including greenhouse gases and reflectivity of the planet and other things. It also allows tests of certain predictions about the dynamics of the climate system. And I'll get into that a little later. It also, of course, allows one to look at the response of other aspects of the environment to the climate change. That is, if you know how big the climate change was, then you can interpret other observed changes, such as increase in the extent of glaciers or changes in the distribution of biota on the planet's surface. Okay, so one thing that I do is I use the polar ice sheets to learn about past climates. That's what I'm going to be talking about. So to make sure you have a good mental image of it, let me show you some pictures. This is the western margin of the Greenland ice sheet, taken from the window of an airplane at about 10,000 feet altitude, looking north along the margin. And if you enter or walk onto the ice here and then head eastward, you go 600 kilometers before you get to the other side. It's a vast cover of ice. And in its central region, the very center looks like this. There's about 3 kilometers of ice stacked on the landscape, and the surface is nearly flat. It's a level place. And these places are in a topographic sense, they're kind of boring. If you want to go downhill skiing, you certainly cannot do so. But they're very interesting scientifically. And let me explain that. So in the central region of the ice sheet, there is an axis along which the direction of the flow of the ice changes. Ice flows as a viscous fluid. It's kind of like, think about it as, honey. If you imagine taking a jar of honey and pouring it out on the table, that would mound up and then spread to the sides. That's what an ice sheet does. Now the ice, of course, is much, much more viscous, so it happens much more slowly, and it can build up a much greater thickness. So in that central axial region, there's a change in the direction of flow. This is a cross-section, idealized cross-section through the center of an ice sheet. The flow on one side is going one way, the flow on the other side is going the other way. And that means that blocks of ice that are formed by accumulation of snow, they get stretched as they sit in the ice sheet. They get stretched because of the flow in both directions. And because they get stretched, they get thinned over time. They also sink down toward the rocky substrate of the ice sheet, which is shown here. So a block of ice that's initially formed like this up top, as time progresses, it will descend in the ice sheet, stretch laterally and thin vertically. And what one can do then is extract a record, let's say by coring. You have to core through the ice and extract a record from this region here. And what that does is it shows you, first of all, that the thickness of these layers of a given time, like an annual layer, they decrease from the surface up here down to essentially zero at the base. The age that is represented, the age that is represented here increases more or less exponentially. So there's a lot of time in the deeper layers and less time in the upper layers. Okay, so this is the basis for ice coring paleoclimate science. You can extract a core from the central region. If you can learn what the age is, which we do through various mechanisms, then we can also measure properties of the ice core to learn about the climate back then and related environmental factors such as the composition of the atmosphere. This is a picture of an ice core coming out of a barrel, and there are some of these ice cores. They all come up in pieces, like anywhere from 1 meter to 4 meters in length. But the longest ice cores that we've taken are about 3.5 kilometers in total length. Not only, well, when you take out an ice core, not only can you study the core, but there's also a borehole that's left behind. And you can make measurements in the borehole, and those measurements can tell you about the ice itself. And this is really the main, or one of the main foci of my research in paleoclimate. You can measure things at depth in the borehole, including the temperature, the actual physical temperature of the ice. So what I'm going to be doing is talking about the temperature history in West Antarctica, as it goes through this transition from the very cold glacial period to the warm period in which civilization has thrived. This is a study it's very analogous to the one Rob mentioned that I did a long time ago. I did one a long time ago like this in central Greenland. That's what he was talking about. I've now applied the same thing to Antarctica, and a couple decades later, the richness of techniques that we can use to study the ice is much greater, much deeper. So it was a much more satisfying analysis. I want to thank all my collaborators. Essentially all of the work that I do is deeply collaborative, and I've got multiple institutions and multiple people. Like whenever I think about my collaborators, I think of this cartoon, and the fact is I collaborate with people because they have useful skills. It's not simply that we like to get together and sip a margarita together. And I'd also have to thank, first of all, the project that I was part of. I was one of about 30 principal investigators in this project called the West Antarctic Ice Sheet Divide Project. And we were funded by the National Science Foundation. And my own work is also funded through a Hewlett Chair by a gift from the Martin Family Foundation, the matriarch of the Martin family being Geraldine Martin, a very cool, socially conscious woman in Florida. Okay, so here's a map of Antarctica. This is West Antarctica over here, and the West Antarctic Ice Sheet Divide site is this right here. That's where this analysis was done. And the analysis uses several different types of data. That I'll show you why these are each important without going into the details too much. It's not that kind of talk. But what's the primary focus of my work is the temperature at depth in the ice sheet, how the temperature varies at depth, which you measure by essentially just sending a very high resolution thermometer down the borehole. So I'll call it the borehole temperature. So that's the first quantity that I'm interested in. And the reason it's so interesting is the following. This is a plot of the temperature at depth in the ice sheet from the surface down to the bed. And you can see it has a profile that looks like this. So it's a bit warmer near the bed because of geothermal heat leaking out, colder at the surface because that's the cold climate. And it has a particular type of profile in between that we understand. Now, this is the profile of temperature that one sees if the climate up top of the ice sheet is constant. If the temperature and the snowfall rate just stay the same up there for a very long time, the temperature profile will end up looking like you see here. What if on the surface of an ice sheet like this, there's a climate change? So let's say the climate had been constant for a very long time, then all of a sudden there's a warming, and that new warm value continues, it persists. What happens? Well, what happens, here's some numerical calculations. I'm going to show two scenarios. They're for different simultaneous changes of the snowfall rate. What happens is that the surface, of course, immediately warms, and then over time, by conduction and flow in the ice, that warm signal propagates down. So here, after 3,000 years, you see that the lower part of the glacier doesn't really know about the climate change, but the upper part has started to warm. And after 10,000 years, the temperature in the upper half of the ice sheet is almost uniform and then warms toward the bottom. However, there's still some wiggles here. And then after 50,000 years, there's a complete adjustment to the new climate. So you get a new temperature profile. And it turns out, of course, that we are now a bit more than 10,000 years after the last major warming on the planet, the transition from the last ice age to the present. So we're in a state that's somewhat like this here, where there are still some wiggles at depth. And those wiggles quite literally show a remnant, a direct thermal remnant of the last ice age. So here's my data and my calculation for the temperature depth profile from this site in West Antarctica. This is elevation above the bed. So the surface is up here, the bedrock underneath the ice is down here. The red curve that you see under here, that's the measurement of temperature, and the blue is the calculation of what that ought to be. Now, the way this analysis works is the calculation is done is adjusted, and it's adjusted and adjusted until one finds a surface temperature history that matches, or that leads to this excellent match to the measured temperatures at depth. This is expanding the upper region here. You can see there's wiggles. Those wiggles are climate change signals. And in particular, the cold here at about halfway down the ice sheet, which is about 1 degree centigrade less temperature than the current temperature here, that is a direct remnant of the last ice age, okay? And by the way, the temperature measurements, which I do in collaboration with a scientist at the US Geological Survey named Gary Clow, that temperature measurement is accurate to within a few millikelvin, that is to say, a few 1,000ths of a degree centigrade. So it's extremely accurate. Okay, and what that does is it allows one to look at how any surface temperature history, a climate history of temperature on the surface, how that creates a profile at depth of the temperature, and then I can compare it to the data and optimize this surface temperature history until that comparison is a very good one, as I just showed you. There's other sources of information that we use. This is a conceptual geography showing how precipitation on the polar ice sheet arises from moisture sources on subtropical oceans, and then a transfer of moisture to the north through the atmosphere. And as that transfer happens, air masses cool, precipitation happens, and that precipitation involves a preferential removal of the heavy isotopes of the water elements. And as a result, the precipitation on the ice sheet is isotopically quite distinct from its composition in the ocean. In other words, the atmospheric transfer of moisture to the polar regions acts like a giant filtration system. And it turns out that filtration system is temperature dependent. So we can measure this isotopic indicator and see that it varies with temperature. This is a global plot of the correlation of the two. Here's a time plot showing these are temperatures of the Greenland surface measured from a satellite varying over some annual cycles. And then here's what the isotopic composition of the precipitation does at the same time. Of course, it shows the annual cycle. It also shows some of these minor subsidiary peaks as well. Okay, so another thing we use from the ice core is a record of that isotopic composition as a function of time. And so we need an age scale for the ice core. We need the isotope measurements. Those are done, or the age scale, I participate in that analysis. The isotopes are measured by people at University of Washington, University of Colorado. And that provides another indicator for the surface temperature. So now we've got two indicators of surface temperature. One is this isotope signal. The other is the borehole temperatures that are measured as part of my project. Okay, there's a third source of temperature history information we can invoke. And this is a bit more subtle. This is a plot of how the density of snow and then ice varies with depth on glaciers. And in the polar regions, the increase of density happens over many meters, tens of meters, okay? And these are two sites, one in West Antarctica, one in East Antarctica, in very cold climates. And in other words, it takes a very long time for snow to convert to ice. The snow falls on the ice surface, and then more snow falls on top of it, compressing it, and then more snow falls on top of that, compressing it more, and so forth. And it turns out that atmospheric gas is not trapped until way down here. So there is a column that is some tens of meters thick in which the gases are free to communicate. And it turns out that the heavy gases, such as certain isotopes of nitrogen, will sink preferentially down to the bottom. They'll pool down here. So you can measure the ratio of heavy nitrogens to light nitrogens and learn how thick this section of snow to ice transition is. And it turns out that transition is climate dependent. It depends both on temperature and on the snowfall rate. This is a contour map showing what that isotopic difference ought to be as a function of both of those. This was done by Krista Bozert at Oregon State. And then this is the black squares. These are the measurements of that isotope ratio for nitrogen in the core, and the red is my calculation of it using my adjusted climate history. So in short, we've got 3 different thermometers here that are functioning, but the borehole temperatures that I measure the isotopes of water and the isotopes of nitrogen. Okay, so I put those all together. There's a lot of interactions in this analysis. And here's the result. This is the temperature in central West Antarctica going from 40,000 years ago toward the present. You can see that here's the heart of the last glacial period, the deglacial warming, and then our relatively equable last 10,000 years or so. So there's a couple interesting things about this from the climate perspective. One is, if you look at this result, you see that the West Antarctica was something like 10 to 13 degrees centigrade colder than it is at present. We can compare that warming to the warming that happened elsewhere on the planet. In particular, so this plot going from 25,000 years ago up to present, the blue is the curve that I just reconstructed for you. That's Antarctic temperature. The red is temperature in Greenland. That's the thing that I did back in the 1990s that Rob mentioned at the start. So my career has kind of done a full circle, although it's spiraling upward, I'd like to think. And then the green are 2 estimates of the average temperature for the entire planet. And you can see that the 2 polar regions, the temperature change was much, much larger. And this is a phenomenon that we call polar amplification. That anytime the planet as a whole, on average, changes its temperature, those changes are much greater, much larger magnitude in the polar regions. And this allows us to quantify that. And this polar amplification is a prediction of climate models as well. This is just one example. Look at the right-hand side here. The projected surface temperature increases for a certain CO2 scenario by near the end of the century. And you can see how there's more intense warming in the high Arctic and to some extent, a lesser extent in the Antarctic here. So that result for the quantifying amplification provides a way to test the climate models. And it turns out that actually it shows the climate models are doing a pretty good job. Here's another interesting aspect of that reconstruction, which is that most of the warming in West Antarctica was accomplished by about 15,000 years ago. And you could see that here in this chart, what fraction of the warming was accomplished by 15,000 years. And my results say about 80%. And that 80% is interesting because as a global average, that increase was only about 50%. In other words, the Antarctic region warmed faster than the rest of the planet. And that too is a really interesting and illuminating indicator of how the climate system functions. It reveals the extent to which, in this case, the cross-equatorial transport of heat in the ocean system differentially warms or cools the 2 hemispheres. And another interesting thing about that, here's a beautiful picture. This is the Torres del Paine region in Patagonia in Chile. And the reason I show this here, first of all, just because it's a beautiful place, but also because there are glacial geologists have gone around the mountain ranges of the southern hemisphere, that are glaciated, which means in Patagonia and in New Zealand, and they have been able to reconstruct the timing of the retreat of glaciers there at the end of the last ice age. And those results show that New Zealand and Patagonia also warmed substantially, or did most of their warming by about 15,000 years ago. So again, it's my result in Antarctica was confirming what this glacial geological data was suggesting. All right, I'm looking at the time, and I think I'm going to skip this. There's more interesting stuff, of course, but just some of the major conclusions of this kind of study, that I'm able to quantify the amplification of temperature changes in the Antarctic. And this shows that on average, actually, climate models do very well with that important aspect of it. And finally, that the early warming, the warming by 15,000 years was quite a bit more substantial in the southern hemisphere than the global average. And that tells us about the importance of the cross-equatorial ocean heat transport. Okay, so now let me step away from that project and talk quickly about some more generalities. I work not just in paleoclimate, but also I study how ice flows, and I study how ice sculpts bedrock landscapes. How ice is able to erode the bedrock landscape. Here's me taking a picture this is in the Milford region of New Zealand. Look at this fantastic glacially carved landscape. I'm interested, how is it that ice is able to transform the bedrock landscape in this way? I'm also very interested in the dynamics of glacial bodies, how glaciers evolve, how they flow. Here's some of my students in Antarctica, a different part of Antarctica, a long time ago, doing sampling of the ice. So my work, it involves several different aspects of glaciology. I'm also interested in the stable isotopes of precipitation for reasons that should be apparent after this talk. I also do some work in watershed geomorphology, the study of hill slopes and rivers. A postdoc working with me and Laura Larson just had a paper accepted in a journal about what controls the sizes of landslides. I'm best known for writing this synthesis of what we know about glacier physics. There's a lot of original research in it. And I just want to tell you that since you always have to plan ahead for the holidays, that if you want to make a good gift for a relative, this is a great gift. And I swear you get a lot for your money. It's a great gift. I also do field education in the geography department. This is me with a field class at Olmsted Point in Yosemite National Park. It's one of the real highlights of my career. Before the pandemic, I was doing this every year in the fall, taking students to Death Valley and the High Sierra and Owens Valley. Here we are walking up a Eureka Dune in the Mojave. There's a group of students in the High Sierra at Rock Creek Lakes. This is the picture that I started with when I reminded you that our planet is habitable only because of the greenhouse effect. These are students in my class. This is me being creative and using the van as a whiteboard because my own whiteboard was getting kind of stained. And this is us in Pine Creek Canyon in Eastern Sierra. We do get donations for the field courses, and I especially thank Jane Sturtzinger and Bob Hink for giving us the most significant donations in this realm. I'm one of the physical geography professors at Berkeley. We have John Chang, who studies climate, especially ocean and atmosphere interactions. Laurel Larson is a hydrologist, also geomorphologist. Jeff Chambers studies biogeography, Amazonia, and fire. Rob Brew studies the biogeochemistry of rare trace gases. And for adjuncts, Dave Wall does biogeography and Mesoamerican antiquity, and Norm Miller does regional climate models and studies fire. We also, of course, have a lot of human geographers in our department. And as a physical geographer, I could say I truly am, and honestly, I'm delighted to be in a multidisciplinary department with a lot of social scientists as well. The interaction is especially useful for students, enriching for students. Okay, so that's what I wanted to say. And let me end it there and turn it back to Rob.
Thank you so much, Kurt, for this wonderful presentation.